Welcome to Study Loop.
So we have a monoatomic gas of 2.8 moles, which has an initial volume of 0.086 meter cubed and an initial temperature of 25 degrees Celsius. It expands adiabatically and gets to a temperature of minus 68 degrees Celsius, and we want to find out the final volume. Now we know that for adiabatic processes, PV power gamma is equal to a constant. So that this is a relation between pressure and volume. But because we are dealing with volume and temperature here, we will try to convert this into a relation between volumes and temperatures using the ideal gas equation. We know that PV is equal to nRT, which means we can substitute for P. We can see that P is nRT by V. By substituting this, we can see nRT by V, V power gamma is a constant. Now N and R are also constants, so we can write T V power gamma minus 1 is a constant. That is it. So we have T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Now gamma, monatomic gases, is 5 by 3, if you remember it. N is equal to 3 for monatomic gases, and gamma is simply n plus 2 by n, where n is the number of degrees of freedom for the atom. Now, for the molecule. So, V2 by V1 power gamma minus 1 is equal to T1 by T2, which gives us V2 is equal to V1 times T1 by T2 power 1 minus gamma. That is it. So V2 is equal to 0.086 meter cube times initial temperature was 25 degrees Celsius, so that's 273 plus 25 in Kelvin, divided by T2, the final temperature was 273 minus 68, whole power 1 minus gamma. I'm sorry, it's not 1 minus gamma, it's 1 by gamma minus 1. So that's 1 by gamma minus 1 is 2 by 3. So that 1 by 2 by 3 is simply 3 by 2. This, when you substitute into a calculator, turns out to be 0.15 meter cubed. So let's look at this before we leave. Let's look at this equation here. So we have V2 by V1 is whole power gamma minus 1 equal to T1 by T2. So we do power 1 by gamma minus 1 on both sides. This way, the powers here cancel and we get to this equation.